Hi everyone, today we're going to be talking about exponential growth and exponential decay. All right, so let's define exponential growth. It's an exponential function and it can be used to solve problems involving exponential growth. So our formula is P at n, or P of n, is equal to P subscript 0, or P naught, times 1 plus r to the exponent n, where Pn is the final amount or amount at n, P subscript 0, or P naught, is the initial amount, r is the rate of growth as a decimal, and n is the number of growth periods. All right, let's take a look at our first example here. There are 5,000 yeast cells in a culture. The number of cells grows by 25% per day. How many cells will there be in 1 week? Okay, so I'm going to start by writing down everything that I know. So I'm just going to list all of my variables. So P at n, P sub 0, or P naught, r, and n. Okay, so I don't know what the final amount will be. All right, so P sub 0 there initially was 5,000 yeast cells. The rate is 25%, so divide that by 100, so 0.25. And n, so days, and this is after 1 week, so there are 7 days in 1 week, so n is 7. Okay, so then we're gonna plug it into our formula. So P at n is equal to P sub 0 times 1 plus r to the exponent n. So 5,000 times 1 plus 0.25 is 1.25, and n is 7. Okay, so go ahead and plug that into your calculator. I'm actually just going to replace this n, before I do that, with 7. Whoops, that's unusual. Okay, so plugging into my calculator, I get 23,841.9 yeast cells. So since I can't count part of a yeast cell because it hasn't developed yet into a yeast cell, I'm actually going to round this down. So therefore, in 7 days, there will be 23,841 yeast cells. Okay, let's look at another example. Okay, the next example. The number of mice in a cage is tripling every week. There were initially 8 mice. How many are there in 6 weeks? Okay, so whenever we see words like doubling, tripling, quadrupling, we have to just think of this as it's going to be 1 plus our r value is going to equal 3 for tripling, or 1 plus r equals 2 for doubling, 1 plus r equals 4 for quadrupling. So if we were to rearrange this and solve for r is equal to 3 minus 1, so r is actually equal to 2. Okay, so let's write down what we know, and I'll show you where that applies. So P at n, I don't know what that is. The initial amount was 8 mice. The rate is the 2, and then n is 6 weeks. Okay, so P at n, so P at 6 is equal to P naught, which is, just gonna plug it in right away, 8 times, actually maybe I will put in the equation here. P at n is equal to P naught times 1 plus r to the exponent n. So P at 6 is equal to 8 times 1 plus r, so 1 plus 2 to the exponent 6, which equals 8 times 3 to the exponent 6. So notice, because we're tripling, we have this 3 here in the brackets, okay? If we were quadrupling, it would be a 4. If we were doubling, it would be a 2. Okay, so plugging this into our calculator, so following rules of BEDMAS, 3 to the exponent 6, and then multiply that by 8, we get 5,832. So therefore, in 6 weeks, there are 5,832 mice. Okay, so let's look at another example here. The number of cells in a culture is modeled by the function P of t is equal to 3,200 times 1.24 t, where t is measured in hours. What is the initial number of cells? So from the equation, we can get the answer as 3,200. So 3,200 cells. What is the growth rate? Okay, so again, from our equation, so 24 divided by 100, 0.24, 24% in other words. Okay, and then how many cells will there be in 12 hours? So this is our T. So if we find P at 12, so 3,200 times 1.24 to the exponent 12. And if we plug that into our calculator, we get 42,287.32. So again, we're going to round down because that last cell hasn't quite fully developed yet. So therefore, in 12 hours, there will be 42,287 cells. All right, next we're going to look at exponential decay. So same formula. The Pn, P0, R, and N all mean the same thing. So exponential decay is an exponential function, can be used to solve problems involving exponential decay. So we're going to first look at half-life. So half-life is the time it takes for something to reduce to half of its original amount. So think of things like coffee or chocolate, or if we're dealing with chemistry, isotopes, they all have a half-life. So after a certain length of time, only half of the original substance will remain. Okay, so example one, we'll save the half-life example for a couple minutes from now. The population of a small town is 4,500. It is shrinking at a rate of 6.5% per year. What will the population be in 5 years? So P at N is what we're looking for. P naught is the initial amount of 4,500. N, so 5 years, and our rate is 6.5. So 0.065 if we divide by 100. Okay, same formula, except instead of plus R, we're subtracting R. Oops. Okay, so 4,500, 1 minus 0.065 to the exponent 5. So that's 4,500 times 0.935 to the exponent 5. And if we plug that into our calculator, we're going to get 3,215.66. So again, because that last person hasn't quite been born yet, or hasn't been quite developed yet, therefore, in 5 years, the population will be 3,215. Okay, so let's look at another example where I give you an equation and we have to interpolate information from the equation. The value of a car depreciates according to the formula V at N is equal to 30,000 times 0.80 to the exponent N, where N is the number of years since purchase. So the purchase price is $30,000. What is the annual rate of depreciation? So this time, 1 minus 0.8 is equal to 0.2, which means we have a 20% depreciation rate. Okay, 20%. Next, what is the value of the car after 5 years? Okay, so we need to figure out P at 5. So that's 30,000 times 0.8 to the exponent of 5. And if we plug that in, we get $9,830.40. So that depreciated quite a bit. And we need a therefore statement, but I'm running out of space. And then last but not least, by how much has the car depreciated in 5 years? So we're going to take our original amount, so 30,000, and we're going to subtract the current value, and that is equal to $20,169.60. Again, we need a therefore statement because it's a word problem, but I'm running out of space. All right, last question. Cobalt has a half-life of 5 years. If you start with 80 milligrams of cobalt, how long will it take for the amount to decrease to 64 milligrams? Okay, so we are actually looking for P, the final amount, the P at N, to be 64. The initial amount was 80 milligrams. So for a half-life, the rate is always going to be 50% or 0.5. 0.5, and the N is we don't know how long it's going to take for this to happen. So P at N, and our formula is P naught times 1 minus R to the exponent N. So 64 is equal to 80 times 1 minus 0.5 to the exponent N. Let me fix that N up here, it's looking a bit strange. Okay, so we're going to do a little bit of guess and check here. So for this course, we don't have to use logarithms. We're just going to use a guess and check strategy. Okay, so the first thing I'm going to do is I'm going to divide both sides by 80. So 64 divided by 80, and then I'm going to be left with 0.5 in the brackets to the exponent N. And if I simplify 64 divided by 80, we get 0.8 is equal to 0.5n, whoops, exponent n. So then I'm going to try to plug in some numbers here. So for my guess and check, so let's say we try 0.8 is equal to 0.5, actually no, let me write it this way. 0.5 to the exponent 0.8, and let's see what we get. So we get 0.57, but I actually need a bigger number. So let's try 0.5 to the exponent 0.6. And that's going to give us 0.66. So our number is getting bigger. We have to get to 0.8. Let's try 0.5 to the exponent 0.3. All right, we got 0.81. Okay, so it's a little too high. So we're going to try 0.5 to the exponent 0.31. So that's still approximately 0.81. So we're going to keep trying 0.5 to the exponent 0.32. And we get approximately 0.80. So 0.32 then is our answer. So 0.32 half-lives to decrease to 64 milligrams. So 0.32 half-lives to decrease to 64 milligrams. So we could times 0.32 by 5 to figure out how many years. All right, that's it for today.